All right, welcome back everyone to my channel. So today we're gonna continue our discussion. So we are still discussing about ACS exam for General Chemistry 1 and 2, and now we are still discussing about the chapter 8. Okay, if you are looking at the ACS guideline, you will see kind of chapter for each chapter that we need to learn and study, right? So now we are still in the chapter 8, okay, which is about um matter, okay, about matter stuff. So yeah, about the matter or yeah, states of matter. So this topic like cover around uh ideal gas, and then kind of like kinetic molecular theory, and this diagram, and uh like what else, like intramolecular force of pure substance, uh and so on. I mean, other more like it cover a lot of topics, but however, I mean, what I just explained is kind of like the summary, all of them in term of state of matter. Okay, so if you are you can find this chapter in our textbook if we are looking at the material like aligned to two chapter. The first one is gases, and then the second one is liquid and solid. So the chapter, the name of chapter may vary or might be different. So just looking at your textbook and then looking the chapter, the name of chapter called gas or liquid and solid. All right. So now we are at the chapter 8. Yeah, let's get started to tackle one by one of the problem. Okay, there is a question here in the study question. A gas behaves most ideally at. Okay, so so the question is about the ideal gas behavior. Okay, the ideal gas behavior. So the key concept here is we need to know the ideal gas law condition. Okay, when we are talking about the condition under real gas behave most likely ideal gas, so we need to assume two things. Okay, the ideal gas. Okay, the ideal gas. We assume two things. So the first one is no attraction. Okay, no attraction between gas. Okay, between gas molecules. Okay, so please remember the behavior of ideal gas. The first one is no attraction between gas molecules. Okay, number two is no volume taken up by the gas particle. Okay, no volume taken up, okay, by the gas by the particle. Okay, but the real gas too. Okay, if we are thinking about the real gas, okay, the real gas to have attraction, as you can see in the our environment, the gas have like attraction each other, and it will take up space. Okay, so to make them act like ideal gas, we need to condition, like we need condition where these effects are minimized. Okay, so think about like this. If we have a low pressure, okay, if we have very low pressure, okay, so low pressure, let me throw it. Low pressure, if we have a low pressure, the particle in gas phase, it will be far apart, okay, far apart. And then the impact is, it will be less attraction, because the distance now is like far away, far apart, okay, far apart. And then if we have condition like high temperature, okay, if we have condition kind of like high temperature, okay, we will have condition like particle are moving very fast, okay, particle moving very fast, okay, particles like moving so fast, moving so fast. So the impact of this one, it will be no time for attraction, okay, no time for attraction. There is not enough time to attract each other, okay. So remember just two concept. If we want to get the ideal case, we have to have no attraction between gas molecule by lowering pressure, okay, by lowering pressure, which is, if we are lowering pressure, we will have a particle like far, like we will see far apart the particle, so the impact is less attraction. And if we have like high temperature, okay, so the particle will be moving so fast, therefore there is no enough time to particle attracting each others, okay. So this is the key of ideal case. All right, so the ideal case condition need to have low pressure and high temperature. Okay, so just so let's eliminate let's take a look at the choice here. Okay, let's take a look at the choice before we have the conclusion of that one. Okay, let's take a look at the conclusion. Okay, the option. The first option is high pressure and low temperature. If we have high pressure, it will the particle will be like much more crowded, okay, and then more interaction, which is incorrect for ideal case. How about the high pressure and high temperature? If we have like high pressure, okay, and high temperatures, so high pressure will be having like a little bit effect of in the ideal case, okay. Low pressure is good, which is what we want to know, okay, which is this one that we want to get, low pressure, okay. But low temperature will increase the attraction. So the ideal one is the part to make a particle like far apart and then moving fast. So the answer will be D, okay. The answer will be D. We have to have low pressure and then high temperature. This is the concept of the ideal case, okay. All right, and then so let's move on to next question. Okay, what is the density? Okay, what is the density of xenon? Okay, of xenon uh, at 70 degrees Celsius and 2.5 ton 2.50 atm atmosphere temperature. Okay, so the key concept, we can use the ideal case, like as you so if we know the equation like PV nRT, okay, PV on nRT, so we have V over here, right? We have V over here. So we need to know first, like, V over here, okay, V over here. So now just arrange this part, nRTP, okay, nRTP. All right. So the issue here is, okay, the issue here is we don't have any kind of information for mole, okay, for mole over here. We don't have any information for mole, okay, and we just have information for the name, like the density, I mean the element itself, and then the temperature and the pressure. Okay, so we know the mr, or molar mass of Xa is 131.3 gram per mole, and then we have R R is 0.0821 liter atom, and then mole Kelvin. And for temperature, it will be 70 plus 273, and then it will be 343 K. Okay, so we just have this one. We don't have any kind of like we have P as well, okay, for the pressure. We have P for the pressure is what is 2.5 atm. So what we gonna do here is we need to determine one by one, like we can like use another way to get the density. Okay, to get the density, we can get the PM, okay, PM, P, which is the pressure, okay, and then this is RT, okay, RT. So this is the volume, right? So as you know, the volume is rho n per v, okay, rho n per v. So to get the if you want to get the v, so how to get this equation, we need to like derive it or break it down. To get such as this equation, you have to plug in such as this way. This is v, so n per row, okay, n per row. So if you using this equation, it will be what? It will be if you want to just P, pressure, okay, and then n per row, right, and then n, and then R, and then T, and then you can cancel out for the n itself, okay. So now you just rearrange this equation to get like rho, all right, and then okay, n per row, so you will get the n. So however here this is gram per mr, okay, and then in this case you can see mole, okay, gram per mr, okay. So rho, and then let me see, rho, and then you will have P, and then RT, Okay, you will have PRT. So let's take a look at this one. And then as you can see, guys, this one, it will be gram per mr, and then this one, it will be gram per liter. Yeah. Okay, gram per liter. Okay. So now we need to cancel out the what we can cancel out here for gram. So gram per ml, gram per ml. Okay. Gram per mr. Okay, let's pause it first. Yep. All right, we continue our discussion now. So let's take a look at the answer of that one. So as you can see in the in the screen, okay, on the screen, that I already plug in some of the I already plug in some of the numbers, and then as you can see that if we use the original equation and then we break it up, like we are going to get this equation, we need to break it down one by one, and then try to derive it one, and then we will get ended up getting like this one. However, we don't need to get kind of this molar mass. Actually, we when we like try to derive it with this equation, we don't get kind of like the molar mass over here. However, if we are looking at the units of the number, we need to cancel out for mole over here, right? We need to cancel out mole over there. So how to cancel out this one? We need to plug in once more. However, assume we don't know about this one, okay? Just in case we don't understand like whether we need to put in the molar mass or not, okay? So as you can see, the just uh plug in for the unit as well to avoid any kind of the mistake. So the purpose we plug the units over here like to maintain or to make sure the unit at the end is the same. Okay, so okay, if we just plug in this number, okay, we just plug in this number 2.5 divided by 0.0825825, and then we will end up getting 30, and then divided by 343. So we will get for the row is 0.08834. Okay, however, remember we just cancel out this one, so we are still having issue for the unit. So for the mole here is liter per mole. However, if when we are dealing with the option, see, the option, all of them still in gram per liter, but we are having issue here liter per mole. Okay, oh sorry, so it should be, oh, it's too big. Okay, it should be let me remove this one, and then it should be mole per liter. Okay, now what we are going to do is we need to cancel out the liter, the mole over here, and then there's an information that we need to plug once more, which is about the molar mass. Okay, rho, okay, 0.08834 still mole per liter, and then times what? Times the molar mass of the xenon. Okay, molar mass of the Xe is 131.3 gram per mole. So we can cancel out for the mole, and then we ended up getting the same units times 131.3. So the answer will be 11.59. So the close one is C, the option C. Okay, the option C. So just remember, we can use just PV equal on nRT. However, when we are dealing with the was that the 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 density, we need to be careful to determine the unit. Okay, we need to be careful determining the unit, because when we having the result like the well, if we are just plug the numbers, we the result like added up like different. Okay, give us a different units with the option. So please make sure the unit should be same. Okay, should be same. All right. So now let's move on to, so we don't need to like use this equation actually, right? Okay, we don't need to use this equation actually. However, just double check your unit before you are choosing the answer. Okay. All right. Now let's move on for next question. A 10-liter sample of ideal gas 25 degrees Celsius is heated at contact pressure until the volume has double. Okay, has double. All right. And then what's the next? What is the final temperature? What is the final temperature? Okay, how to deal with this question is pretty easy. We have information what it is. Volume is 10 liter. Temperature is 25 plus 273 for the Kelvin. Remember, we always use the Kelvin. So it will be 298 Kelvin. And then is heated at constant pressure. So pressure is P1 and P2 is same until the volume is double. Okay, the V2 is 2V1. Okay, until the volume has double, so which is 20. Okay, 20. All right, so what we can use here is we can use the Charles law. Okay, since the pressure constant, we use the Charles law. Okay, what, so is, I think we still use the same concept, PV nRT, PV nRT. However, this is 1. Okay, 1, this one is 2. Okay, now we don't care about the what we don't care about the R, right? We can cancel out this one, and then we can the question is about is heated. Okay, the final temperature. The question is the T2. Okay, P1 is constant, so we can cancel out the pressure, and we can cancel out the N because the sample itself is same, right? So now the remaining equation is just V1 V2 T1 T2. Okay, this is the Charles law. Okay, now just plug in one by one. V1 is 10, V2 is 20, T1 is 25. How about the T2? Okay, how about the T2? So just 10 T2 and then 25 times 20. So it will be 10 T2 and then 500. T2 will be 50. All right, T2 will be 50. So just 50. Just remember, in this case, the question is in the degrees, the degree Celsius is, okay, in the option is in the degree Celsius, right? In the degree Celsius. So just remember, still in degree Celsius, not in the Kelvin. So which is the answer should be A, right? The answer should be A. Hmm? 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 What's wrong? Oh, sorry. Sorry. Oh, yes. We have to convert it first to Kelvin, okay? Sorry. 10, 20, and then yeah. Oh yeah, sorry. This is Kelvin, okay? T2. So what's the answer? Let's see. Times 20 and then 10. So 596. Yeah, this is the Kelvin, and then to get the answer is, nope, T2. Okay, to get the Celsius. Okay. Yep. Okay. Now we're getting the answer of this one. All right. So let's move on to next question. What's the volume of CO2 measured at 0.993 atm, 28 degrees Celsius, must react in order to completely consume blah 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 and blah blah blah. So now we having kind of like much more complicated question. However, this one is still not difficult to solve this problem as long as we understand the concept of mole. Okay, as long as we remember the concept of mole. Right? So let's get started. Okay, so now the question is about the volume. The ATM is this one and this one must complete. Okay, the consume. Okay, so now we have information, this one and this one, molar mass. So let's like mole gram per mr, gram per mr. 59 divided by 101.96. Okay, 59 divided by gram per mole. So we will getting about 0.579 mole. Okay, Al2O3. Okay, so this one is 0.579. The question is the CO2 itself. This one, the coefficient is just 1. Okay, using the stoichiometry to get mole. Okay, so 1 mole of Al2O3 equal 3 mole of CO2. So we have 3 mole of CO2 times 0.579, which is we have 1.737 mole CO2. Now, how get the volume? Just simply using the PV and RT. The question is about the V. So now we can solve the problem. 1.737 R is 0.0, right, 0.0821 times T is what it is, 28 plus 273 is 301, and then divided by 0.993. Okay, times 0.0821 times 1.733 divided by 0.993, 43.12 liter. Okay, just quick heads up that we need to consider or double check for the units. Okay, just remember, just quick heads up, remember for the unit, because sometimes unit will give us like more information. Okay, more information. In this case, as you can see, this one is small, right? And then for the R, it will be mm, liter. Okay, liter like the previous one, guys. Okay, liter ATM mol key. I don't remember. However, I don't remember. I'm not remember that one. However, it will be in the liter mol Kelvin. Okay, ATM. It will be in the ACS list. Okay, there is a table or like box containing those information about the units. Okay, to help us get much more information. All right, this one is Kelvin, right? This one is ATM. So we can cancel out one by one now. ATM, and then this one is small, right? Oh yeah, mol. Can cancel out this one to this one, this one to this one. So the remaining unit is liter. Okay. So now move on the other part. Okay. If the diagram shown is representative of particle is sample of ideal cases, which statement is true? Okay. So just the concept. Okay, just the concept that the ideal case mixture. Okay, the ideal case mixture. Okay, P total. It will be PA plus PP plus PC. So each partial pressure, it will be proportional. Okay, it will be proportional to the number of particle. Proportional number of particle. Okay, so the more particle, the more particle will be producing more pressure. More pressure or more partial pressure. Okay, so now let's take a look at this one. A has the largest partial pressure. How many A? Just okay, A is 4. Okay, how about the B? 1, 2, 3, 4, 5. So I think the B has the largest partial pressure. So the answer will be P. Okay, so just remember the concept of partial pressure is proportional the number of particles. All right. So now let's move on to next question. So now we know the concept of like the number of particle, much more particle, much more partial pressure. And then now we are dealing with another concept again. The rule here is, okay? The rule here is at the same temperature, okay? At the same temperature. You see? The question is the graph to represent 4 different cases at the same temperature. The like cases or the lighter cases, okay, move faster, okay, then heavier. Okay, this is the key. Okay, this is the key. So at the same temperature, this is the concept. The lighter case will have a faster speed, okay, than heavier ones. Okay, just remember this one. So now let's take a look at the option F2. If we are looking at the molar mass, okay, if we are looking at the molar mass, F2 is just 38. Okay, molar mass. This is the concept. Okay. Actually, we have a specific equation like this one, RT, and then this is MM. However, I don't like this equation because if you are dealing with the exam, okay, sometimes we don't remember the equation, okay. However, this is 3RT, okay, sorry, 3RT mm, where mm is molar mass. Okay, just knowing the general the general concept, like at the same temperature, the lighter molar mass, the lighter particle will move faster than the heavier ones. Just knowing this concept, we can solve this problem. Okay, F2, and then again CO2. How many molar mass is 44. Cl2 70.9. Kr is 3.8. So now, which one the correct level? Okay, as you can see, guys, which one the highest speed? The highest speed is one. This one, right? So one will be F2, and two will be CO2. 3 will be Cl2. 4 will be Kr. Okay? So, because as you can see, this is the lowest speed. Okay, the lowest speed. So, the answer will be D. Okay, the answer will be D. And then after checking the answer, this is the number what? Number 6. The correct choice is, oh, wait. The correct choice is will be what? So speed is unproportional with like opposite with molecular mass. Okay, so inversely proportional. The higher molar mass, the lower average speed. Therefore, the correct choice will be what? The curved one. Hmm. Oh, okay. This is the highest one, right? This one, the highest one. Highest speed. It can achieve highest speed. Okay. Okay, highest speed over here. Okay, so I think we make wrong over here. We made something wrong. It should be the 4. It should be F2. 3, because the highest speed is over here in this part, right? See, if we are looking at the Gaussian over here, see, this is the speed, and then this one is the Gaussian will be here. This one it will be here. Okay, number 3 will be let me see. The faster one is CO2. Sorry. Number 2 is Cl2. For the one is Kr. So the answer will be C. Okay, the answer will be C. Just remember that concept. Okay, now let's move on to another question. Just remember that the lighter will be faster. Okay, this is the concept in, I mean, in our daily life, like which one the lighter one, probably it will be faster than the heavier one. if they have the same energy. Okay, if they have same energy. Okay, let's move on to another question. Which correctly shows a hydrogen bond between two molecules of methanol? The hydrogen bond is represented as dash line. Alright, so the key concept of hydrogen bonding is hydrogen hydrogen bonding. Hydrogen bonding. Okay, hydrogen bonding is the covalently bond to highly electronegative atoms such as O, N, and F. Okay, so there will be the option. Okay, there will be the bonding between H and O, or an N and F. Okay, let me reply one first. All right, now let's move on for the second criteria. So the hydrogen is attract to the lone pair. Okay, so attract, the hydrogen will attract it to the lone pair. Okay, on O N A V. Okay, near atom nearby. Okay, so let's see. So the for methanol, the relevant atoms, okay, like OH group is the hydrogen donor, the oxygen of another methanol is the acceptor. Okay, so let's evaluate one by one the option. Okay, let's evaluate one by one the option. So for the option A, see, the bonding is between carbon and nitrogen. Sorry, carbon and hydrogen. So It should be not. Okay, because it should be H, O, F, or N. Okay. How about the option C? We are moving to option C first. Okay. So the dash line from oxygen to hydrogen. Okay. The oxygen to hydrogen. So it is like it's backward. The hydrogen should be donate. Okay. The hydrogen should be donate. Okay. Or donor. Okay. So over here, the oxygen is donor. Okay, so this one is like opposite. So that's wrong. Okay, the option C. Oh, sorry. Wait. The option C again. Dash line from oxygen to hydrogen on carbon. Okay, CH. Oh, in this case, CH not involving. Okay, in hydrogen bond. Okay, so because of the CH, so it will be wrong. And then again, for the option D, H and H, it should be not. Okay, so the last option is only P. Okay, the last option is only P. Okay, so the option E, the interaction between carbon and hydrogen. So this one is not hydrogen bond. The option C has the interaction between oxygen and okay, has the interaction with oxygen correctly, but the wrong hydrogen, because it's bonded to carbon, not the oxygen. Okay, it should be in the oxygen. As you can see, the option P, the option P is methanol with this one, right? Okay, so you know that the hydrogen bonding specifically is to 2% NOF, right? Bonded to hydrogen with lone pair of electron. So as you can see, in this case, this is minus, right? O is minus, and then this one is plus. Okay, this is minus, this one is plus. So the interaction is we need to know that the NOF will be bonding with the hydrogen with a lone pair electron of this one. Okay, so like I mentioned, attract to the lone pair on nearby. So as you can see, guys, as you can see over here is like there is a much more, yeah, over here. Okay, there is a atom that attracted. Okay, attracted over here. So yes, we done for this question. So what's the difference is between C and P is there is a interaction over here. However, it bonded with carbon, not with the oxygen. Okay, if we are dealing with like the plus and minus, it will be plus, it will be minus, and then this one it will be minus, and doesn't make sense. Okay, it should be one is plus, another one it should be minus. Okay, that's good. So now moving to another question. What is the correct order? What is the correct order of boiling point? Okay, it's the correct order of this boiling point? Increasing normal boiling point. Okay, so to determine the boiling point, we need to understand the concept, the structure, like intermolecular force, and then relationship between the the strength of intermolecular force and boiling point. Okay, so let's break it down first. So what's the key concept over here is stronger force. Stronger force will be need more energy needed to break them, which is higher boiling point. Okay, now let's take a look at one by one the option. Okay, and then we have once more we have a concept, London dispersion have less effect with the dipole. This is the type of the intermolecular bonding. Okay, intermolecular bonding, or intermolecular force. Polar forces. This is the concept. Dipole, and then again ionic bond. So now let's take a look at the option. PR, okay, PR, okay, it will be non-polar, right? Non-polar. Okay, it will be non-polar. Okay, so it only has the London, okay, London dispersion. So which is very weak. Okay, which is very, very weak. Okay, just non-polar molecule. This is the lowest one. PR2 is the lowest one. So PR2, the lowest one, probably. And then ICL, okay, ICL has the same thing with the PR2, however, it has different, okay, it has different different type of the intermolecular force, which is this is the polar, okay, polar, because it has different kind of electronegativity, right, between both. And then it has also dipole, okay, stronger just than dispersion. So ICL will be higher than PR2. And then NaCl, we know this is what is ionic. So NaCl, the highest one. So the answer will be PR2, ICL, and NaCl. So the answer will be A. Okay. Okay. Just quick information that intermolecular force is the attraction between different molecules, okay? not within them. Okay, so they don't make molecules, but they hold them together in liquid and solids. Okay, the stronger intermolecular force, the higher boiling point. So as you can see, van der Waals is London dispersion force. Okay, a temporary or weak attraction. Okay, and then caused by random movement of electrons. Okay, so non-polar molecule, like, so all molecule have this. Actually the all of the molecule have this one, but non-polar molecule like Pr2O2 CH4 rely on them exclusively. All right, and then dipole force, attraction between polar which have positive and negative ends like magnet. Okay, and then another one like hydrogen bonding. This is the 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 strongest one. And then another one is ionic bond. Okay, the ionic bond, like plus and negative. Okay, I'm still trying to remember this one. Intermolecular forces is van der Waals. All right, so the weakest one, or London dispersion, and uh hydrogen bond, the strongest one. This one is easy for remember. And then dipole, right? Dipole. I'm still trying to uh I'm still trying to get a way to remember easily. Hmm. Okay. So now to identify for the intermolecular forces, we have a way to determine easily like step by step. So first one is look for the hydrogen bonding, whether the hydrogen bonding percent or not. Okay, is a hydrogen bonded to F, O, or N? Is there another F, O, N nearby to interact with, something like that? And then is the molecule polar? Okay, molecule polar. Okay, as are their polar bond. Okay, are their polar bond, which is big electronegativity difference. So like we are dealing with, this one is polar because it has like electronegativity difference between both, right? So we can know that is the molecular polar. If yes, it has dipole moment. Okay, it has dipole force. Okay, or we can say is the molecular like asymmetrical, so dipoles don't cancel. If yes, yes. Okay, so Cl and I have electronegativity difference, right, between both. So we can conclude it has dipole moment. Okay. For PR2, it's highly symmetrical, right? It's highly symmetrical because it's same. Both are it's same. So like like the another way number three. So is the molecular is non-polar, which is all atom it's same, or it is symmetrical, such as CO2. CO2 is symmetrical, right? COO, it will be symmetrical. So if that just only has the it has dipole moment like CH3, Cl, and other stuff. All right, so recognition. Oh, okay. So I don't even know. All right, and then the last one is ionic. For ionic, I'm pretty sure you are understand. Okay, metal and non-metal, or positive and negative ion. Okay, just remember for two concept. So whether to determine it has dipole, whether the dipole moment percent or not, we need to know concept the electronegativity difference and the concept of unsymmetrical. If they are having the electronegativity difference, it will have dipole moment. Number two, it whether the molecule or the molecule has the symmetrical or not. Okay, if symmetrical and has the electronegativity difference, so it will be dipole interaction, which is much more stronger than only what van der Waals. For van der Waals, it only have polar non-polar bond. Okay, non-polar bond, which is no have no difference for the electronegativity. Okay, all right, so we done, or like highly symmetrical, something like that. All right, now let's move on to another equation. Again, the two vapor pressure curves A and B are shown. One is for methanol and the other is for 1-hexanol. Which statement correctly completes the sentences? Curve A is hexanol because hexanol has weaker intermolecular force than methanol. So let's discussing this part again. So we are dealing with the size again. So the difference between both significantly is about size. Okay, intermolecular force, and then uh like the size. Okay, so as you can see, guys, CH3OH, do do they does it do they have, or do they have the hydrogen bonding? Yes. Hydrogen bonding? Yes. Do they have the dipole moment? Like I mentioned, it has a different electronegativity. It is. Yes, right? Do they has the dispersion? Okay, dispersion? Yes. Do they has dispersion? Yes. Okay. So like I mentioned before that uh London dispersion percent in all molecules, okay? Only force in non-polar molecules, okay? So it will be always in the was that in the all molecules, okay? Dispersion, yes. And then how about the 1-hexanol? Same. It does it has hydrogen bonding? Yes. How about the dipole? Yeah, dipole, yes, because it has different electronegativity, right? And yeah, let me replay someone. Diba? All right. So yes, just a recap. Both have same intermolecular force. Okay. The different thing here is just one thing. What is that one? Is the mass. Okay, is only the mass. Okay, like I mentioned, greater mass. Okay, greater mass will be stronger intermolecule intermolecular forces. Okay, intermolecular forces. So again, the key concept is the uh the greater mass, stronger intermolecular forces. Okay, because it's harder for molecule to escape into vapor. Okay, so stronger intermolecular forces is which means harder for molecule to escape into the vapor. Lower vapor pressure. Weaker intermolecular force, easier to escape, higher vapor pressure. So as you can see, curve A, it should be hexagonal. Lower, so it will be lower vapor pressure. So hexagonal, curve A is hexagonal because one hexagonal has weaker intermolecular forces. No, curve A is hexagonal because hexagonal has stronger. Yes, hexagonal is stronger than methanol. Let's see for the curve. So as you can see, when we increasing more, okay, the pressure is still around less than 100. However, for the so like this hypothesis that the lower vapor pressure, okay, so B would be hexagonal, I believe. Will B will be hexagonal, and then A will be methanol. Okay, so curve A is methanol. Okay, because methanol has weaker. Okay, this one is also correct. So the answer probably is C. The answer probably is C. Yes, that's true. The answer is C. How about the A? A is incorrect because hexagonal has greater intermolecular forces. And then B is incorrect. Okay, because curve because the hexagonal should be a sign for P curve. Okay, a sign for P curve. And then D is incorrect. Okay, A is methanol because methanol has stronger. No, this one is not correct. Is incorrect. Is incorrect. So assign curve A as methanol. Yes, because it has lower intermolecular forces. Yes, and curve B is hexagonal because it has higher intermolecular forces. Like I mentioned, guys, mass, like greater or stronger intermolecular forces, which is lowering vapor pressure. So to escape one molecule, it will be much more difficult if we have like bigger size. Okay, to escape one molecule into vapor, okay, it will have so it will be having lower vapor pressure, okay, because it's harder for molecule to escape into vapor. So the vapor itself will be so low, it's too low, because it will be still in it quite difficult to escape into the vapor. Okay, I got you. So vapor pressure, if we have a bigger molecules, it will have like uh it will hard it will be harder to escape one molecule into the vapor, so which means it will lowering the vapor pressure. So now let's move on for another question, which is about the vanadium. All right, for vanadium. Vanadium crystallized in polycenter cubic lattice with unit cell H length of 305 pm. What is the density of vanadium? Okay, so eq- this question is talking about density of unit cell. Okay, so we need to use the density is Z m and divided by Na times a cubic. Okay, so Z is number of atom and m is molar mass. Na is Avogadro number. A is H length. H length in centimeter. Okay, so let's take a look at the answer. Step 1, vanadium. Okay, polycenter cubic lattice. So Z is 2 atom, okay, per unit cell. As you can see, this is 2 atom over here, so it will be only 2, right? It will be only 2. Okay, so Z, because BCC, it will be 2 atoms per unit, and then alpha, or A, each length is 305 pm, which is 3.05 times 10 minus 8 centimeter, and then molar mass is m itself is what, 50.94 gram per mole. So just plug in one by one the number. The density is what? Z is 2, and then m is 50.94, 3.05 times 10 minus 8 times what? Avogadro number is uh 6.022 times 10 23, right? So it give us the number 250. Okay, it will be give us is the final result will be 101.88 minus what, 1.71. This one is 3, right? Okay, so it will give us this one, and then the density, it will be 59.6. However, this is still in the mole, okay, mole, not per centimeter cubic. So we need to put it in the centimeter cubic. So it's already converted. Wait, it will give us like 5.96 gram per centimeter cubic. Yes. So just remember the equation: density Z times smaller mass divided by Avogadro number times what it is, length. Wow, this is quite complicated. So there are three common of unit type too. Oh, okay. For simple cubic, simple is 1 for Z, right? Okay. For PCC, put the center cubic lattice, it should be 2. And then FCC, okay, fast center cubic, it will be 4. Okay. Okay. Just remember this equation, okay? If we have kind of like this equation, this information. A pure substance is initially 365 K and okay, and then all right. So just remember guys, the concept of phase diagram. Phase diagram in chemistry. Just want to take Google it. And then see, in this part it should be gas, right? And then over here it should be liquid. Over here it should be solid. Okay? So just now uh just illustrate the question. A pure substance is initially 365 over here and 45 4 545 Thor might be here, and then 360. Okay, it might be over here, right? What happens to the substance when the pressure is increased to 760 at constant temperature? So moving on over here. So now it will be in the liquid. Okay, it will be in the liquid. The substance boils and become a gas. No, the substance meltings. Okay, not melting. It's not melting actually. Actually, it's not melting. I think because it's not in the solid, right? It should be in the gas. The substance is sublimes and becomes gas. Nope. The substance condense and becomes liquid. Yes, that's true. Become liquid. So the answer will be T. Just remember the concept of the phase diagram, and then we can solve this problem easily. Alright, now we have the real question, and then I need to take a break, and then we will start again later on to deal with the real question.